Today we are going to discuss orbital speed. What is orbital speed of a satellite? What is its expression? We'll also see what is the time period of such satellites. What is the height of such satellites there when they have been put in a particular orbital speed. We'll also obtain the expression for the angular momentum of such satellites and also the total energy of the satellites in such orbits. After that, we'll discuss what is geostationary satellites. What are the conditions for a satellite to be geostationary? And we'll see what is the height of a geostationary satellite there. So all these we'll discuss in today's discussion. Orbital speed. It is the minimum speed of a body or satellite orbiting around a heavenly body or Earth. This is the minimum speed that is to be supplied to the particular satellite there or any other body. Suppose m is the mass of the heavenly body or Earth, around which we have another body m whose mass is m, and it is orbiting in orbit of radius r, and suppose its velocity is v. So here we have assumed that the distances are from the center of the heavenly body or Earth. So if it is orbiting around it, definitely it will be moving in a circular path there, and here the centripetal force will be there which is required for its motion around the heavenly body. So that will be given by the gravitational force of attraction. So here, if I assume that the force of gravitational attraction, this will be force of gravitation, that will be equals to gmm by r square. That is the force which will be acting on the body of mass m. Centripetal force, this will be equals to mv square by r, and this centripetal force is provided by this gravitational force of attraction. So definitely in equilibrium these two will be equal. So in equilibrium, gmm by r square is mv square by r, or we can write v equals to root over gm by r. This is the expression for orbital speed of the body in an orbit of radius r. Remember, in this expression there is no term of mass of the body which is orbiting. So that means this is independent of mass of the body orbiting around the given heavenly body, or suppose if we take satellites, then in that case it will be independent of mass of the satellite. It will be depending upon the mass of the source body under whose gravitational attraction it is orbiting. So it will be the mass of the heavenly body or mass of the Earth there, and of course the distance between the heavenly body center and the mass which is orbiting around it. That is the another body which is orbiting around the given heavenly body. And r is the distance between the body which is orbiting and the center of the heavenly body. Now here, if I assume that this r is nearly equals to capital R, which is the radius of the heavenly body or Earth. So in that case, this expression will be how much? It will be nearly equals to gm by capital R. That's the expression. So here, this capital R is the radius of the Earth. And this particular expression, if you consider, this will give you the value of the orbital speed for the object which is orbiting very close to the surface of Earth. And remember that this radius of the Earth is 6400 kilometer. So in that case, whatever height at which you are taking, just near the surface of the earth, so that that particular height can be neglected in respect to the radius of the earth, then in that case this will give you the orbital speed for the object orbiting very close to the surface of earth. So even 10 kilometer, 20 kilometer, if you consider, in that case we can assume that it is negligible as compared to the radius of the earth. So that we can substitute here. So this is the expression. Another form what we can get, you know that acceleration due to gravity on the surface of earth, this is your gm by r square. That means for gm I can put g into r square. So if you're substituting this one, then what will get for v? It will be equal to g r square by r, and that is your g into r. This is the another form in which orbital speed can be expressed. That means now it is in terms of acceleration due to gravity on the surface of earth and also radius of the earth. Of course, that we could have put here also. Like here, if I substitute, it will be your g r square by r. Remember, this r is radius of the orbit of the satellite there or the object. That means this is not equal to r. This will be your g r square. If I assume that it is at a height h, that means if I assume that this particular distance from here to here, if I assume that this is your h, then that we can substitute here. And of course, this g is your acceleration due to gravity on the surface and r is the radius. So this is another form in which orbital speed can be expressed. Suppose we want to find time period of revolution of such satellites or the body. So the time period of revolution, if I represent it by say capital T, this will be given by this length of the path in one full rotation. If you consider, it is the circumference of the orbit there. So that is your 2 pi r divided by the speed with which it is orbiting. So we have already taken that this is the orbital speed. So this will be your small v there. So here we can put that this is your 2 pi, r is there, and for orbital speed it was your gm by r. So this can be written as your 2 pi root over r cube divided by gm. So this is another form in which we can write for the time period, and this r we can also write as r plus h divided by gm. So this is the expression for time period of revolution. Of course, if I assume that object is orbiting very close to the surface of earth, in that case, if h is negligibly small, in that case time period will be how much? 2 pi root over r cube by gm, and this is equal to 2 pi root over r cube. Gm we can write as gr square. So this is equal to 2 pi root over r by g. So this is the time period of revolution of the satellite very close to the surface of earth. So this is the expression for the time period. Now we know the radius of the earth, we know acceleration due to gravity on the surface of earth. In that case, this we can calculate and it will be roughly 84 minutes. So the time period is 84 minutes for the satellites orbiting very close to the surface of earth. So this is for satellites orbiting close to surface of earth. So for that case, we'll get that one roughly equal to 84 minutes. Another term we can try to find out, that is the altitude of the satellite. that is the height of the satellite from the surface of Earth. So again, if I assume that it is at a height h and capital R is the radius, in that case we have seen that force was equal to GMM by R plus h whole square, and this we can write equal to the centripetal force, and which is written as your m omega square R plus h. So this can be written, m we can cancel from both sides, that is the mass of the satellite there. So it is your Gm by R plus h whole cube. This is equals to omega. Omega can be written as your 2 pi by t whole square. So this is your R plus h whole cube. If I suppose take this side, in that case it is your Gm. This term Gm is here, divided by 4 pi square, and this t square term will come here, so into t square. This is the expression for R plus h whole cube, because that term we have taken this side. So in that case it is a Gm into t square, 4 pi square will be in the denominator. So R plus h, this is your Gm by 4 pi square into t square whole power 1 by 3. Or if you take h, this is your Gmt square by 4 pi square whole terms power 1 by 3 minus r. So this is the expression for the height of the satellite from the surface of Earth, or altitude of the satellites, you can say. Of course, this expression what we have taken in the previous derivation for the time period, we have already obtained the expression for the time period. So from that also you can get this, because the time period term, if you consider, we have already derived. That was your 2 pi r by v, and the expression for v we have got, this is the square root of Gm by R plus h. So again you will get 2 pi R plus h whole cube divided by root over Gm, and this is your power 3 by 2 here. Because if you take this term in the numerator there, in that case it is under a square root sign, and this is your R plus h, so it will be equal to R plus h power 3 by 2. This is exactly the same term. If you square it, you will get this particular expression, because in that case you will be getting there Gm into t square, this 4 pi will come here, and now it will be your R plus h whole cube. So this you can use it to find the height of the satellite. Suppose you want to find angular momentum of the satellite. Angular momentum we can get as mvr. It is mass of the satellite, v is its orbital speed, and r is distance or the radius of the orbit. So this term, if you substitute, it is m. For v, we have already substituted the expression or got the expression as root over Gm by r. This is your r. So in that case, it will be equal to m into root over Gm. Now this term will be under square root sign. So this will be equal to angular momentum L. So it is your m into root over Gm r. Next, suppose we want to find energy of the satellites. So for this, potential energy, if you consider, this will be how much? Minus Gmm by r, gravitational potential energy, it is there. Another term is there, that is the kinetic energy, which is equals to half mv square. So now we have the potential energy, this is the kinetic energy. We can find the total energy just by taking their sum. Of course, here for v square, if you substitute, it is your half m. Now v, orbital speed expression, we have taken root over gm by r. So in that case, it will be simply your gm by r, as v is your square root of gm by r. So now if you consider the total energy, then it is your potential energy plus kinetic energy, which is minus gmm by r plus gmm by 2r, this term. So this is your minus gmm by 2r. This is the total energy of the satellite in its orbit. So this is your minus gmm by 2r. And this negative sign is indicating that the satellite, while being in its particular orbit, it has lost energy. Its energy is this much less. That is why it is in a particular orbit there and it is orbiting. If you want to make that one free so that it goes out of the gravitational field, then you need to supply this much amount of energy so that its total energy will be 0, and then it will be at infinite distance there, and it will not experience any gravitational force. Geostationary satellite. A satellite which remains stationary with respect to a particular point on the surface of Earth is called geostationary satellite. That means this is a satellite which will always be overhead a particular point on Earth's surface when it is in its orbit around the Earth. Suppose, for example, we take satellite is suppose here, and this is the particular point, it is just overhead it. So now if suppose Earth is rotating about its axis and the satellite is revolving around the Earth, and if it is such that in its entire motion it is always overhead that particular point, then that particular satellite will be called as the geostationary satellite. Now there are certain conditions which is required for a satellite to be geostationary. So if you consider the conditions for the satellite to be geostationary, the first condition is that the time period of revolution of the satellite must be the same as that of rotation of the Earth about its axis. Like here, if I assume that the Earth is rotating about its axis, it takes 24 hours time. So in the same 24 hours duration, the satellite also must complete its revolution around the Earth. Then only it will be always overhead a particular point. Like if suppose I assume that this particular point is there, above which we have the satellite there. So satellite is suppose here. This is the satellite. Now if I assume that Earth is taking 24 hours time, so after 12 hours this particular point will be somewhere here. So the satellite will also complete its half revolution around the Earth. So the satellite will reach to this point. Again, if you consider that in one full revolution, it is taking 24 hours time. So in 24 hours time, again the satellite will be here and the particular point will also reach to the same point here. So in the entire motion, if you consider suppose after 6 hours, then this particular point will be somewhere on this side. Satellite will also complete 1/4 of its revolution. So it will be overhead there. So that is why if you consider that the period of revolution and the period of rotation is same, in that case, it will always be overhead. So this is the first condition for a satellite to be geostationary. The second condition is the sense of revolution of the satellite must be same as that of the rotation of the Earth. Suppose we have taken that the time taken is same. It is 24 hours duration. But suppose if I assume that Earth is rotating about its axis in this direction, say it is the west to east, and the satellite is revolving in opposite direction. So if suppose I assume that Earth is rotating in this direction, satellite is moving in opposite direction to that. So what will happen? just after small duration of time, the particular point here on the Earth's surface will move somewhere here, whereas this particular satellite will take position here, because they are moving in opposite direction there. Their sense is opposite. So in that case, it will not be overhead. Of course, in the entire duration of one time period, that particular satellite will be only twice just overhead the particular point, one here and after 12 hours, that is after half revolution. But for the rest of the time, it is not overhead that particular point. So obviously that particular satellite will not be called as the geostationary. That is why it is required that the sense of revolution of the satellite must be same as that of the rotation of the Earth. Third condition is the satellite must revolve in the concentric and coplanar orbit in the equatorial plane of the Earth. So the particular satellite must orbit in a concentric and coplanar plane lying in the equatorial plane of the Earth. Then it will be geostationary. Otherwise, you just imagine that the Earth is rotating like this and the satellite has an orbit whose time period is 24 hours. It is also revolving, say, in the same sense. That means revolution and rotation is having same sense there, but the satellite is orbiting in this direction. Earth is rotating in this direction or in this particular axis, and the satellite is suppose revolving in this particular direction. So obviously it will not be geostationary. So here it is also required that you can also say that the axis of rotation and revolution must coincide. When it is suppose concentric and coplanar, definitely that axis of rotation and revolution will be coinciding there. So these are the three conditions a satellite must obey or satisfy so that it is geostationary. Now there are many uses of geostationary satellite. It is used there in communication purposes there. It is most extensively used in this particular field. Let's now see what is the height of geostationary satellite and how we calculate it. Now for this, we can take that suppose if it is at a height h above the surface of Earth, and there the centripetal force which will be acting, that will be given as your m omega square r, and this will be provided by gravitational force of attraction due to Earth. So if you now consider the gravitational force of attraction, this is your gmm by r plus h whole square, because r is the radius of the Earth and h is the height above the surface of Earth where that particular satellite is located. This is equal to centripetal force. So it is your m omega square r plus h. These two should be equal. Gravitational force of attraction and centripetal force. So now here m will get cancelled, and what will get? Gm by r plus h whole cube. This r plus h will come in the denominator here, and this is your omega square, that is your 2 pi by t whole square. Or what we can write, r plus h whole cube, this is your gm t square by 4 pi square. Obviously r plus h, if you consider, this is your gm t square by 4 pi square, and this term's power will be 1 by 3 because it was cube here. So now if I consider h from this expression, it is your gmt square by 4 pi square power half minus r. This will give the expression for the height of geostationary satellite above the surface of Earth. So if you substitute the values of g, m, t square and then r, of course t here is the time period of revolution. 24 hours we know. We'll have to convert it in suitable unit there. That means you convert it in second there. And then this mass is there, mass of the earth, universal constant of gravitation, radius of the earth. If you take that one as 6400 kilometer, then finally you'll get this value of h to be 36,000 kilometer. This is the height of geostationary satellite above the surface of earth. So mathematical expression, if it is required, you can find from this one. And if you want to calculate the exact value of the height there, substitute the values there of g, m, t and r, you'll get the height as 36,000 kilometer. So this is there for geostationary satellites. We also have sun synchronous satellites. These sun synchronous or polar satellites, they will be basically orbiting in the polar axis. That means it will be orbiting in this axis from north to south direction. Earth is rotating about its axis from west to east direction. This will be moving in the north to south direction. The orbit of such polar satellites will be lying in the perpendicular direction there to the equatorial plane there. These satellites are roughly about 500 to 800 kilometer height from the Earth's surface, and their time period is roughly about 100 minutes. And these satellites are very useful as they will pass through a particular point in one full rotation there. So in that case, these can be used for the weather forecasting there, or for monitoring, for scanning Earth there. So these find also very extensive use there in day-to-day life. So such satellites are the polar satellites or sun synchronous satellite.